Hi everybody, this is Hava Blair from the SNAP Plus team, and today I'm here to tell you a little bit about the Wisconsin Phosphorus Index and let you know how we run these calculations behind the scenes in SNAP Plus, and also some recent updates that we've made to the Phosphorus Index and the data that goes into it. So many of you might have heard about the Wisconsin Phosphorus Index, or the PI, and it is a model that estimates phosphorus delivery from the field to the nearest surface water. So here we have this diagram of our field. We have surface runoff carrying a certain amount of sediment and dissolved phosphorus, and then we have that yellow arrow representing the pathway from the edge of the field to the nearest surface water. Now, most people are familiar with the Wisconsin Phosphorus Index through SNAP Plus for nutrient management planning. So when you're looking at SNAP Plus and you're on the cropping screen like this one, you can see the phosphorus index, or PI, value on the right side in the rotation settings panel. And so that's the same place that you see your T value and your average soil loss. And you see there's a line there that says average P index. The P index is calculated as an average across the rotation that you have set for the field. One thing that you might not know about the P index is that we also calculate it year by year. So here I'm showing a zoom in on the cropping page where we're looking at two crop years, 2023 and 2024. At the very bottom, you can see in the yellow box that I have a total PI line, and then I also have a particulate, or part PI, and a soluble or dissolved PI row. So those two components together, the soluble and the particulate, those are two pieces that go into calculating the total PI. And we'll talk about the third piece in a little bit here. Now, the phosphorus index is one type of phosphorus management strategy that can be used to follow the 590 nutrient management standard, which we've also heard about in presentations as part of these regional meetings. To give ourselves a visual of what we're talking about here, I wanted to put up a couple pictures. So when we're thinking about phosphorus loss from a field, the phosphorus index specifically calculates surface losses. So we're interested in this process where runoff can carry both dissolved and sediment-bound phosphorus from the field. And that's what we're seeing in this picture here. And then once that phosphorus in those two different forms gets to the edge of the field, we also know that there is some pathway, and this differs for every field, between the edge of the field and the nearest waterway. So here we can see we've got the arrow indicating that there's some pathway, some slope and distance that phosphorus has to travel before it actually gets delivered to the nearest surface water. And since what we're interested in here is keeping the phosphorus in the field and out of the waterway, we know that thinking about the differences between different fields and how much phosphorus might be delivered is an important part of this. So the first thing I want to share to you about updates in the phosphorus index has to do with data and what kind of data we're using behind the scenes. One important thing to know about SNAP Plus version 3, which is the web version of SNAP Plus, is that we have recently updated all of the soils data. So we had been working with 2019 soils data for quite a while, and that's still the data set that exists in SNAP Plus version 2, the desktop software. But we've most recently updated to the 2024 soil survey data in SNAP Plus version 3. So it's possible that when you log in, you might see some different soil symbols and some slightly different soil data because of that update. The second important data component that has been updated in the P index recently is our precipitation data. Now we'll talk in a little bit about what we use precipitation data for, but the important thing for you to know here is that we've updated it to be an average, and our database to be an average of the last 20 years, so the most recent 20-year period, which means that we're looking at precipitation data from 2004 to 2024. And I'm showing up here on the screen that the previous data set we were using had been the 20-year period from 1996 to 2016. And then finally, the third bullet point on this slide indicates that for the rest of the presentation, I'll be talking about some different research-based updates that are happening to equations within the phosphorus index. And I'll indicate those on the following slides with a star to let you know what are some of the different parts of these equations that we've updated based on research that has been conducted in Wisconsin. Now, when I go through and talk about these different P-index equations, I'm going to break it up into three different pieces. The first piece, the first two pieces, in fact, are sediment-bound phosphorus and dissolved phosphorus, and those two together comprise the field edge runoff losses that we're calculating in the Wisconsin Phosphorus Index. The second piece, which is the middle box on the screen, is thinking about that pathway that the phosphorus takes from the field to the nearest water, and we call that the total P field-to-stream delivery ratio. And I'll describe that in more detail in future slides. Those things together, the sediment-bound phosphorus, the dissolved phosphorus, and then this delivery ratio, are the three key things that we need to calculate that annual P index value. Now let's start with the particulate-bound or sediment-bound phosphorus. I have a simplified equation at the top of this slide, and this is showing that to calculate particulate phosphorus, we need two important things. We need some idea of the phosphorus concentration in the sediment, and we need an estimate of how much sediment is leaving the field. Now, for the first piece, which is the phosphorus concentration or content, we are calculating in the phosphorus index an adjusted surface soil test P and organic matter, and we use that to estimate soil total P. So we can take information from your soil test and from the organic matter and estimate what is the soil total P that we have. The second important piece here is that particle size is really, really important when we think about phosphorus content. So we know that the smaller soil particles like clay and silt, they tend to be enriched in phosphorus. That means that they have a higher phosphorus content relative to the soil as a whole when we just look at all of the particle sizes together. This is one thing that has been updated based on recent research. So we have updated the enrichment ratios for the clay and silt particles, and that controls about how much phosphorus those different particle size classes are contributing to that total P. The bottom part of the slide in the purple text is showing that when we estimate the amount of sediment that's leaving a field, that would be the second part of this particulate P equation, we're using Russell II, which is the revised universal soil loss equation 2. And this model allows us to calculate an average soil loss for a field, but another thing that we can get from the model are these different particle size components that are important for this calculation. So we've got the clay, the silt, the small and the large aggregates, and sand. So we're looking at how much sediment of each of these different particle size classes is leaving the field. Next, we can think about dissolved phosphorus, and here I have an image to help us think through the different parts of this. So you can see I have these raindrops falling on my field, and that is the precipitation. And then we have three different sources, potential sources of dissolved phosphorus in the field. So that rainwater has to interact with some source of phosphorus in order to dissolve it and then carry that dissolved phosphorus in the surface runoff. The soil itself can be a source of phosphorus, so you can see that here we have some soil P concentration, and we can know about that from your soil test values. The other two important pieces are any phosphorus that has been added in manure or fertilizer applications to the field. So here you can see I have what is supposed to be a surface application on the field of manure, and so we can think about when you have precipitation falling on a field, and some amount of that precipitation might run off, what's on the surface is interacting with that water and potential runoff water, and that can dissolve phosphorus and carry it in the runoff off the field. So the phosphorus index is accounting for these different sources of dissolved phosphorus, and there's a few things to know about how we do this. The first is that estimating runoff from rainfall is an important part of this equation because we need some water to carry that dissolved phosphorus. When we calculate runoff, the method that we're using, the type of equations that we're using, are called a modified curve number method. And to use this method, some key inputs that we use are numbers called runoff curve numbers that we can get from Russell II. And it's nice to get these from Russell II because what Russell II allows us to do is account for lots of different important field conditions that we know make a big difference in terms of runoff. So thinking about things like residue, and how rough is the surface from different tillage operations, and is there a growing crop at that time. The second important input when we're calculating runoff are those 20-year precipitation values that I was describing earlier in the presentation. So we have a database that is looking at average seasonal precipitation over a 20-year period, and also the distribution of precipitation events. So how many different types of event sizes do we have across these 20 years on average? The thing that's new here with the way that we're calculating dissolved phosphorus is that we have a new method for winter runoff, And the important thing to know about that method is that it's now consistent with the modified curve number method we use in the spring, summer, and fall seasons. So in the p-index, we're always calculating runoff on a seasonal basis, and we're using this method for winter runoff that allows us to account for the fact that we know in the winter less water is going to be able to infiltrate due to frozen soil conditions, and we want to account for that when we think about how much water and runoff is available in the winter. All right, another important update here that is relevant both to the soluble or dissolved phosphorus and particulate phosphorus is how we think about the amount of surface nutrient applications, so that could be fertilizer or manure, how much of those surface applications remain on the surface after you go through a later tillage event. So here I'm showing a table with all these different types of tillage systems that are in SNAP+. And then the second column is the fraction on the surface. Fraction on surface means how much, what fraction of that phosphorus, if you had put on a surface application, would still be there if you do the tillage in that given row. And this recognizes that these different tillage systems, they have different levels of soil disturbance, different levels of soil mixing. And so what we're trying to get at here is the fact that when you bury a phosphorus source like fertilizer or manure, that makes it less available for runoff to interact with or less likely to be eroded from the surface of the field. And so that we're expecting less of that phosphorus to leave the field. Now, the final part of the equation that I want to talk about here is this field to stream delivery ratio. And this is getting at that pathway between the field and the nearest surface water. So we use this to account for the fact that we know that there is phosphorus deposition and infiltration that can happen for both the sediment and the dissolved fractions in that pathway from the field to the stream. And so we need to account for that and recognize that some fields are very close to the nearest streams and some fields are very far away. And so we need some way to account for those differences and recognizing that that has an impact on the total amount of phosphorus delivered. So the way that we account for this is using some modeling data that we have that looked at different lengths and slopes of that pathway, assuming a channelized flow in something similar to a grassed waterway, which we know is not perfect, but it's kind of the best we can do under these conditions. And then we look at how much phosphorus is delivered if at different distances and different slopes. And so if you're a SNAP Plus user, you've probably seen this data on the fields page when you see the columns distance to perennial water and slope to perennial water. Those are categories that we use to get at the fact that we expect different amounts of deliveries under different conditions. So I want to sum up some of the recent updates that I've just talked about. Early on, I described phosphorus enrichment ratios for clay, sand, and silt, and that's an important part of how we calculate particulate P. Now, the changes that I described, what is the impact on your phosphorus index results? For these P enrichment ratios, in general, the updates mean that the particulate P fraction is generally going up because the clay and silt enrichment have increased based on data from Wisconsin soils that we've collected. Now, the second two changes for winter runoff and the amount of phosphorus remaining on the surface after incorporation, those don't have a clear answer. So it's always going to be variable depending on your starting point. And when we look at winter runoff, that change in the calculation impacts the dissolved phosphorus component. And whether or not your phosphorus index number might go up or down with these changes really depends on your county level precipitation. So this is going back to the fact that we use the 20-year winter precipitation averages when we're calculating winter runoff. So depending on what exactly the precipitation in your county looks like and how it's changed since that last data update, this could go up, it could go down. It's really going to depend on your starting point. It's the same for the amount of phosphorus remaining on the surface after incorporation. That particular component of the model has an impact on both the dissolved and the particulate P fractions, and it really depends on which of those tillage categories you're using, whether you see a large increase or a decrease in your phosphorus index. Now that I've talked about all these different equations that are happening behind the scenes, I also want to remind you that when we are making these types of updates to the phosphorus index, we're always doing it in the context of testing these changes against actual field data. So we're lucky in Wisconsin to have networks of field edge monitoring data that allow us to look across different soils, across different cropping systems, and compare When we have measured data for how much phosphorus actually left a field from one of these monitoring stations, we can put those same conditions into the Wisconsin Phosphorus Index and see how well we do, and find opportunities in places where we are estimating phosphorus loss well, and then places or cropping systems where we need to do better and make some changes so that we're lining up with actual field data that we're observing out in fields. So I want to also recognize just an incomplete list of phosphorus index contributors. So a lot of different researchers and faculty have contributed to the phosphorus index and to helping us make these improvements over time. And I want to recognize a subset of them here, and also that I've probably missed some folks. Thank you for your attention today, and I'm sharing my contact information on the screen in case you have any questions going forward.